I am actually re-recording this podcast because there was a lot of ambient noise in the previous recording I did. It's October heat and I don't run the AC, so I'm relying on a fan. Somehow the noise crept into the recording, but now it should be okay. This is a nice news type of article about the revolution in car batteries by Nicola Jones, who writes very well. Uh, so here are some electric vehicles charging in a car park in the UK, which will ban the sale of petrol and diesel cars in 2035. You may have heard that the UK also shut down its last coal power plant. Of course, we have to wait for the winter and see how gas supplies may affect this decision and so on. Electric car battery revolution, alternatives to lithium ion cells could power future electric vehicles. I met Nicola Jones in 2011 when I was being trained as a Aldo Leopold environmental leader by Woods Institute of Stanford. But anyway, there is a revolution brewing in batteries for electric cars. Japanese car maker Toyota said last year that it aims to release a car in 2027-28 that could travel 1,000 kilometers and recharge in just 10 minutes using a battery type that swaps liquid components for solids. Chinese manufacturers have announced budget cars for 2024 featuring batteries based not on the lithium that powers today's best electric vehicles, but on cheap sodium, one of the most abundant elements in Earth's crust. And a US laboratory has surprised the world with a dream cell that runs in part on air and could pack enough energy to power airplanes. Right? Airplanes get a lot of bad rap for producing emissions per person that can knock off your entire year's carbon budget if you made a long distance flight. These and other announcements rely on alternative designs to the conventional lithium ion batteries that have dominated EVs for decades. Although lithium ion is hard to beat, researchers think that a range of options will soon fill different niches of the market, some very cheap, others providing much more power. We are going to see the market diversify, said Gerbrand Cedar, a material scientist at the University of California, Berkeley. The pursuit of better car batteries is fierce in large part because the market is skyrocketing. More than a dozen nations have declared that all new cars must be electric by 2035 or earlier. The International Energy Agency forecasts that the global stock of EVs on the road will rise from 16.5 million in 2021 to nearly 350 million by 2030. You still have to look at what percentage of the total car market that is, but that demand for energy for from EV batteries will reach 14 terawatt hours by 2050, which is 90 times more than that in 2020. That's the IEA forecast or projection. Car batteries have a stiff list of requirements. They need to pack a lot of energy into as little material and weight as possible so that cars can go farther on a single charge. They need to provide enough power for acceleration, recharge fast, have a long lifespan. The common standard is to withstand 1,000 full recharging cycles, which should last a consumer 10 to 20 years, the economic considerations. And of course, they have to work well across a wide range of temperatures and be safe and affordable. It's very hard to optimize all these things at once, says Linda Nazar, Nazar, a battery researcher at the University of Waterloo, Canada. Sorry for mangling your name, Linda. Electrode revolution is already on the way. Batteries are effectively chemical sandwiches which work by shuttling charged ions from the one side to the other side, the anode to cathode, through some intermediate material which is being used, which needs electricity, like recharging your phone or whatever else. So the electrolyte is the intermediate material. So electrons flow in an outside circuit through something, and recharging the battery means shunting the ions back to the anode from where you discharged it. With such troubles plaguing batteries with better electrodes, Many say the most enticing solution is to replace the liquid electrolyte with a solid one. So here is how the any battery works. Conventional lithium-ion batteries share some common features and materials. Lithium ions move from the anode through an electrolyte to the cathode during recharging, right? So they move back, sorry, I read it wrong. Lithium ions move from the anode through an electrolyte to the cathode. During recharging, they move back to the anode. Rechargers are exploring ways to improve battery design, including 6 options shown here. So I hope this is correct, because the electrolyte, so yeah, so lithium ion will move from here to here, and that produces electricity. So you have an external circuit. Basically, when you connect your phone, that's completing the circuit to move the ions, which is what electricity is. When you recharge, those ions have to go back, right? So that's the idea. What are the improvements needed or being designed? Add silicon to the anode. Typically it's graphite. Swap to a lithium metal anode. You'll see in a minute. Thirdly, use a solid electrolyte instead of a liquid one. We'll see why. Swap to a sulfur cathode. We'll see what advantages there are. Metal oxides, including elements such as manganese, cobalt, and nickel, are used now. Use sulfur from the air itself as one of the cathode ingredients. Imagine that. And swap lithium to sodium to reduce costs, because sodium is abundantly available. Lithium, there is enough, but it's cornered by a few countries. So this solid electrolyte is a solid idea. The idea of solid state batteries is to use a ceramic or solid polymer as the electrolyte, which hosts the passage of lithium ions, but helps to stem dendrite formation, which happens in liquid electrolytes. Not only does this make it easier to use an all lithium anode with the attendant energy density advantage, but getting rid of flammable organic liquid also means removing a hazard that can cause fires. The cell architecture of solid state batteries is simpler than that of liquid based cells, says Nazar. And the solid batteries in theory work better both at low temperatures, because there is no liquid to get more viscous when it's cold, and at high temperatures, because the interface with the electrodes don't suffer so much when it's hot. So I'm getting confused with Nazar and Najar, because I have a friend at Penn State, Ray Najar, whose name is spelled N-A-J-J-A-R, Najar. I'm sure this name is related or the same source. It's spelled N-A-Z-A-R, Nazar. Okay. Price drop. Of course, the battery prices have dropped as the quest continues for miracle batteries that pack in ever more energy. Some scientists argue that the most pressing concern is the need to pick a battery chemistry that will be cheap and sustainable in the long run. So you want to reduce the cost, as we'll see here in a minute. Lithium ion battery types. A variety of cathode materials are used, each with pros and cons. As we'll see later, they want to reduce all the cons. So nickel, cobalt, aluminum oxide, or NCA, 8%. Other 2%. Nickel, cobalt, manganese oxides dominate at 60%. So that is NCM that's shown here. Energy density is good, but it's not so optimal for cost and power, safety, lifespan, and performance at extreme temperatures. Okay, NCA is doing well on energy density, but also poor on other things. This is kind of a spiderweb diagram that's helpful. And you have 30% of lithium ion phosphate cathode material, and LFP has not as good energy density as the other two, but it does well on power, safety, and lifespan. Okay, so pros and cons. The powering up, of course, is for research that is pushing up energy density ever higher in all the battery types, with some extremely high possibilities. But these can come with some trade-offs on price and other performance measures. So existing batteries in blue and future potential shown in dashed arrows. For reference, energy density of petrol in cars is at 1700 watt hour per kilogram. So if you look at the conventional lithium ions, the original Sony lithium ion battery was at 120, and it has some potential, not so impressive. The sodium ion battery is at 160, but also has a good potential. So this is the energy density here. And silicon anode, so you see what happens, lithium metal, lithium sulfur, so you can see the increase with other materials with lithium. But solid state here already has 390 in terms of watt hour kilogram density, and has a potential with experimental result for lithium air solid state cell coming in at 680. Projection for lithium air solid state cell comes in at 1200, which is less than 1700, but obviously we want to phase out petrol internal combustion engines because they are terrible for the environment and for us and for all the other species as well. So we may have to live with lower energy density, but there are many other ways like reduced engine weight, reduced overall weight, and cleaner atmosphere, cleaner water, cleaner, calmer climate, right? So guess and test. Battery development is onerous because the behaviors of materials are not always predictable. Rupp, another scientist, says, for instance, that it currently takes researchers 8 to 15 years to come up with new solid-state electrolyte designs and optimize the specifications, including which additives to use and how to pack in high densities of lithium. This gives me, as a material scientist, 2.5 more materials to work on before retirement, says Rupp, and that's too slow. Assistance is coming from artificial intelligence and automated synthesis, which can help to explore more options more quickly. For example, the DOE, Department of Energy Pacific Northwest National Lab, PNNL, in Richland, Washington, is working with Microsoft to rapidly come up with new battery materials. A lithium-sodium solid-state electrolyte found this way is now in initial tests. So all the big corporations like Microsoft, Amazon, Facebook, Google, Apple, they are very keen on energy, renewable energy, battery technologies, etc., because their cloud services, which make a lot of money for them, are energy guzzlers, water guzzlers. They are even going for nuclear, okay? But these AI strategies are limited by the information that chemists have to feed into them, says Nazar. I'm having really Nazar. There are still plenty of unknowns. Sorry, Linda. There are still plenty of unknowns, she says, about what's actually going on at the atomic level at the interface of electrode and electrolyte materials. Okay. In the end, experts say we are likely to see a range of batteries for our future cars in much the same way that we have 2, 4, and 6-cylinder engines today for internal combustion cars. We might see sodium ion batteries or LFP, lithium iron phosphate. Yeah, what was it? Lithium iron phosphate. I don't know why it's called LFP. F is ferrous, iron is F, chemically speaking. Forklifts or specialist vehicles, for example, then there might be improved lithium ion batteries, maybe using silicon anodes or rock salt cathodes for mid-range vehicles, or perhaps solid-state lithium batteries will take over the mid-range as well. Then there might be lithium sulfur or even lithium air cells for high-end cars or flying taxis. But there is a lot of work yet to be done. All of the different chemistries that aren't commercialized today have their pros and cons, says Cunningham. I don't know if it's Cunningham or Cunningham. Our job is to remove all those cons and just try to increase the pros. Flying taxis, of course, is a good idea because right now we have world full of traffic jams because we only go around in two-dimensional space. If we use the third dimension into the air, maybe we can fly around and get there quickly without traffic jams either. But I'm sure if everybody starts flying around, there will be other issues. We already have helicopters flying around, but they are incredibly inefficient in terms of a technology. And they say never use a helicopter even when there is no option. But I don't want to get into trouble with helicopter people. So let's leave this here for now.